Okay, so in this video we're going to continue computing derivatives of exponential and logarithmic functions, but this time we're going to do them for slightly more complicated looking exponential and log functions. So remember these two formulas we had from the last video. The derivative of b to the x is equal to itself times a little bit of extra. So how does that go? The derivative of b to the x is b to the x times ln b. Okay, that's that. And when you take the derivative of ln x, it's always equal to 1 over x. And if you want to plug in negative numbers, you put the absolute value there, and it still doesn't change the derivative. So derivative of the absolute value of x, of natural log of the absolute value of x, is 1 over x. All right, so let's do some examples now that look slightly different from those two formulas. For example, e to the 5x. What's the derivative of that? Well, my claim is we can still use the formula, but we have to change things around a little bit. All right. In other words, let's use some properties of exponential functions to help us get it to the point where we could just straight up use the formula. All right, so e to the 5x. It looks like the base should be e. All right, that's what it looks like it should be. But it turns out that if we use that as the base, we won't be able to use the previous formula, which has the base here, but you see the exponent is just the variable it's by itself. And in this example, the variable is not by itself. It has a 5 next to it. So look what we do. We rewrite e to the 5x as e to the 5 to the power x, right? And now the thing inside the parentheses is the b, and the exponent is all by itself. Okay, check. So now when we go ahead and take the derivative of that, we should be getting, how does the slogan go? Itself times ln of the base. In this case, it's e to the 5th power. But look further, this is e to the 5x, just putting it back together. But ln e to the 5th, what can you do with the exponent? Bring it out to the front, times ln e. But ln e is equal to 1. And so the final answer is e to the 5x times 5. All right, not bad. So that is how you do that one. All right, just moving some stuff around using basic properties of the exponential function. How about the next one, ln of 5x? Obviously, the 5x x isn't inside the log by itself. There's a 5 next to it. So how do we do it? Well, first you should break it up because you know multiplication inside a logarithm is addition out. It becomes addition outside the logarithm. So ln of 5x is equal to ln of 5 plus ln of x. And so now when you take the derivative of both sides, okay, equal sign got a little covered there. What do you get? So remember the derivative of that whole thing. You get, well, what's the derivative of the first thing? ln 5 is just a number. So actually that goes away and it's just 0. And then what's the derivative of ln x? It's just 1 over x. And so you see the 5 didn't matter at all. Let's just write a final answer here. d dx of ln 5x is equal to 1 over x. The same exact thing it would have been if the 5 wasn't there at all. Remember, our formula for log right here. So let's go do some more examples. Here's another one, e to the x plus 1. It looks almost like it'll fit the formula, but not exactly because the exponent is x plus 1, not just x. But there's a quick fix for this. What does it mean to take e, or a base, to the exponent x plus 1? It means raise it to the x power and then multiply it by e, right? Because taking exponents is the same thing as repeated multiplication. So now it should be easy because now you have a number times an exponential function. How do you take the derivative of that? All you do is you ignore the number out in front or in the back. It doesn't matter how this thing is, right? Because it's just a constant. And you take the derivative of e to the x, which is just itself. And so you get e to the x plus 1. All right, and that's it. So that was pretty simple. You got to be a little bit careful if this base changed to, let's say, a 3. And then you'd have to add the little bit of extra. Okay? So just remember, when you take the derivative and the base is not e, there's going to be a little extra factor, and that factor is ln of the base. Okay, so let's go here to another example with logs. We have ln of x squared. Again, it's a little different because x isn't all by itself inside the log, it's x squared inside. And how do you do this? Well, you just have to remember that ln of x squared, what can you do with the exponent? Put it in the front. So you get 2 ln x. And so when you go and take the derivative of that, you get, well, you ignore the 2 out in front because that's just a constant. So you get 2. And what's the derivative of log? It's just 1 over x. And so you get 2 over x as the final answer. Okay? And so just to summarize what we've done derivatives of functions that look like e to the rx plus p. So e with a linear function in the exponent. And we saw that this is just going to be itself, okay? Just like how the slogan has been going all this time. So itself, e to the rx plus p. And then what's the thing that comes out in the front? Times r. That's the little bit of extra. All right, so nothing complicated there. How about ln of r times x to the power p? So we put everything together, and what do we get? Remember, this number out in front doesn't matter at all. And what happens to this number p? It just comes out to the front. So you simply get p times 1 over x. That's what the derivative is. And so there you have it. These are derivatives of exponential functions, slightly more complicated exponential and logarithmic functions.